Chapter 9 Optimization. Optimization is to find a maximum or minimum of a function. So this function we call is an object function. And for maximum and minimum, I need to mention this just find local minimum and local maximum. Usually. Then at maximum or minimum point m, then partial f by partial x1 at the point m equals partial f by partial x2 equals partial f by partial xn equals 0. So first partial derivative at the point m is 0. To find a maximum or minimum, so usually we use this algorithm. So steep is descent algorithm. Assume there's a 3-variable function. So f, x1, x2, x3. Then the gradient of f. So this is the gradient. The upside down triangle is for gradient. So the gradient of f or the third f equals partial f by partial x1 times e x1 plus partial f by partial x2 times e x2 plus partial f by partial x3 times e x3. So from this formula, e x1, e x2, e x3 are the unit vector in x1, x2, x3 dimensions, respectively. So their f, the gradient f, is a vector. This is important. It's not a number. It's a vector. And at this point, so starting point, so ending point actually, so x1 0, x2 0, x3 0, then we can calculate this gradient. So the f at this point, so points in the direction of the maximum rate of the change of the f function with respect to the distance. And then we define a unit vector EG by gradient. Okay. EG equals the f over absolute the f. Just remember, gradient of f is a vector, then divided by length. So this absolute of a vector is the length of this vector. So we get the unit vector EG. This is Lewis vector. So where absolute of the gradient f, we can from this formula equals square root of the partial f by partial x1 square plus partial f by partial x2 square plus partial f by partial x3. Okay, so this calculates the length of the gradient. Then to find a local minimum, this is important. This is local minimum. So start at a point and move in small steps, delta f, in a direction of the steepness. So which is the minus EG. Then x, so x is the vector again, the point. Okay, next point. So x n plus 1 equals xn minus EG times delta. Just remember, delta x is that. So xn is the current point. Xn plus 1 is the next point from the gradient. Then this is just remember, this is the 3-variables function. So x1 n plus 1 equals x1 n minus So this is the delta f partial f by partial x1 at the current point over the gradient, the length of the gradient at this point times 1. Similarly, x2 xn plus 1 equals x2n minus the partial f partial x2 at this point then over the length of the gradient times 1. x3 n plus 1 equals x3n minus partial f by partial x3 at this point over the length of the gradient at this point. So from these three formulas, we can get the last form. Now, this is example function. So example function just two variable function. So f xy equals 4xy squared minus 4x1 x2 plus 2x2 squared. Two variable function. First, we need to get the partial derivation. Partial f by partial xy equals 8x1 minus 4x2. Partial f by partial x2, so this constant now, so go here, so this is the minus 4x1, then so I can plus 4x2. We assume start at this point, so 2, 3, x1, comma 2 equals 2, comma 3. Delta S equals 0.01. We could use a smaller number, maybe 0.001, so we have the most to get a local minimum. And a maximum of 10,000 iteration. So this means we need to find the local minimum in the 10,000 iteration. Otherwise, the code will set we couldn't find a local minimum. Okay, so now go to next. Okay, so clear all, close all, COC. First step, so delta S of ds equals 0.01. Maximum iteration, so maximum underscore iterations equals 1.034. So we know this is the 10 power 10,000. The initial point, so x0 equals 2, 3, 2 variable functions, 2 numbers for initial point. X equals x0. Then first record this function. So fx comma dx fx. So fx is the current point result. dx is for derivative, partial derivative, equals fx 1 to x. So let's go to this first. I didn't upload this one. Okay. So open this file. So function f dfx equals fx 1 to f. So this is the original f. We go to here. Okay. I cannot use this. Okay. Maybe use the full screen. Okay. So now just remember this. So this is original f. So f equals 4x1 squared here minus 4 times x1 times 2 plus 2 times x2 squared. So this is the original function. And the dfx, so is the partial derivative, first order partial derivative. So first one, define a column vector. So dfx equals 0, 2, 1. Then dfy equals, so this one, 8 times x1 minus 4 times x2. dfx2 equals minus 4 times x1 plus 4 times x2. So this one defines the object function and is the first order partial derivative. So return values is current function result and also is the first order partial derivative. Okay, so quote this function at the initial point. This one, so we get the initial fx and the initial partial derivative. Then for I equals 1 to maximum equation. This is the tensor form. First one, we need to calculate the gradient. So G gradient F and the score MAG is for the length, the magnitude is for magnitude, equals square root of the d fx1 square plus dfx2 square. So this is the length of the gradient at the current point. Then we need to calculate the last point. So xn equals 0, 2, 1, xn1 equals x1 minus dfx1 over gradient underscore magnitude times dx. xn2 equals x2 minus dfx2 over gradient and square magnitude times dx. So this is from this function. You remember, just from this function. This is for 3 variable function. We just have the 2. So just use the first 2 formula. Oh, okay, need to change. Okay, so now we get the next point, xn. Then quote fx12 again. So we get the current fxn and also is the derivative partial first order partial derivative dfx. Then we need to check if fxn great than fx. This is the last point. So this printf minimum is found after the %d. This is for the integer iteration. So this is for this one minimum. So this is the title here. So break, then stop the current the loop. Else, so this means fxn is less than fx. Okay. Then x equals xn and calculate this object. So take this one. So and so now this is loop. So go back to 4 here, then keep going until fxn is greater than fx. So we know the last point, fx, is the minimum value. Then after this one, so you check I first. So if I is greater than or equal to maximum iteration, so print f print f, error no solution. Otherwise, for else, so f minimum equals f print f, so now print out the all value. X1 equals percent 10.5 f. So 10.5, so this is for float number, so decimal point number. So use 10 spaces. And digits after decimal point, we use the 5 points, 5 spaces. So they will show 5 digits after decimal point. X2, so equals the same format, percent 10.f. Then minimum value, so equals percent 10.5x. Backslash是在 2 so x1, x2, and fx. So this is for the steepness, the descent algorithm. In MATLAB, so it's also has a function. So this is for MATLAB function. F meaning search. So call this function, so we need to use original object function. So this we define. So you can use add, get the original is the function. Then S0, so this is the starting point. Then the result will find the minimum point and also the minimum solution. So f print f from the f mini search backslash n, f print f, so the same x1, x2 minimum. So this is x21, x22 minimum 2. So this is from the MATLAB function. So these two results should be close. Then for this one, xy equals mass read minus 0.5 column 0.1, then column 1.5. So this is create a 3D grid. This number you need to check. So this is the starting point, this end point. This actually from our calculation before. This is the starting point. For I equals 1 to length x, so from this one, for j equals 1 to length y, then j dij dx equals fx1 to x1i y j I. So this creates the stick. Then mass x y stick result. So this will show the 3D map. Okay, so let me run this. First one, let's show this 3D. So this the 3D, so I think it's the surface 3D for the fx. So you can see minimum should be around this point. Right? Go up in x1, go up in x2, go up in x3. So minimum is around this point. Then go to your command window. This will show. Okay. So first one is we from the steep east the descent method operator. So we just use the 362 iteration with the difference. So x1 equals 0.0069, x2 equals 0.00112, and the minimum is 0.008. Then for F mini search, this is the MATLAB function. So you can see x1 equals minus 0.0003, x2 equals minus 0.005, minimum, F minimum. So you can see for this one, the MATLAB function F mini search has a higher resolution. If we check with the original object function, so you can see square passive, the minus a number. So from this one, so we can guess 0 should F equals 0 should be the E. Then if we go to our steepness descent method, if we choose the smaller step, then we can get a higher the resolution result. So let me run this again, but we get more time and more time. So you can see now this is we get the higher resolution result. So now, yeah, iteration number is also 10 times, but now it's 3. Okay, so this is this one. Then go to homework. Homework is similar. So homework still is the two variable function. So f equals 4 plus 4.5 x1 minus 4 x2 plus x1 square plus 2 x2 square minus 2 x1 x2 plus x1 to 4 to power 4. Then minus 2 x1 square x2. Then we can get the partial division. Partial f by partial x1 equals 4.5 plus 2x1 minus 2x2 plus 4x1 could be minus 4x1 2. Partial f by partial x2 equals minus 4 plus 4x2 minus 2x1 minus 2x1. Starting point is 6 delta S is 0.01, and the maximum iteration is the 10,000. Okay, so for this one, you need to define fx12 by yourself according to the this object function. Okay, and another thing you need to change is this one, mass read. So you also need to change this one according to your function. Actually, you can just run this first, use your own function, use the homework object function, and then look at the 3D figure and change. You need to change the starting point and also and okay, so this is the optimization.